In this episode, we are going to sort out three ideas that often get blended together even though they are not the same thing, and that confusion can lead to weak security decisions very quickly. Embedded systems are everywhere. Industrial control systems, ICS, run many of the physical processes modern life depends on, and the Internet of Things, IoT, fills homes, offices, vehicles, and industrial spaces with connected devices that quietly exchange data all day long. At first glance, they can all look like small computers placed inside larger devices, so beginners often assume they belong to one broad category with roughly the same risks and defenses. The problem is that their boundaries matter because the purpose of the device, the kind of environment it operates in, the way it connects to other systems, and the consequences of failure can be very different. A smart speaker in a living room, a sensor on a factory line, and a controller inside a medical or industrial device may all involve embedded computing, but they do not create the same security questions. Recognizing those boundaries helps you understand where safety, reliability, privacy, and network exposure start to diverge instead of treating every connected device as just another small computer. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at CyberAuthor.me in the Bare Metal Study Guide series. A good place to begin is with the broadest category, which is the embedded system. An embedded system is a computing component built into a larger device to perform a dedicated function, often with a narrow purpose and with very little direct attention from the user. Unlike a general-purpose laptop or desktop, an embedded system is usually not meant to do anything the owner wants on demand. It is designed to carry out a specific role, such as regulating temperature, controlling a motor, reading a sensor, displaying status information, locking a door, managing battery use, or helping a vehicle component behave correctly. Many people interact with embedded systems constantly without even noticing them because they live inside appliances, cameras, elevators, printers, routers, cars, industrial devices, and countless everyday tools. From a security perspective, that matters because the computing function is still real even when the device does not look like a computer in the usual sense. Once software, memory, inputs, outputs, and communication capabilities are present, questions about access, integrity, updates, and misuse begin to matter whether the device looks familiar to a security team or not. ICS is a more specialized category with a stronger connection to physical operations, industrial processes, and environments where timing, stability, and safety carry unusual weight. These systems are used to monitor or control equipment and processes in places such as manufacturing plants, utilities, pipelines, water treatment environments, transportation systems, and other operational settings where digital instructions affect real-world machinery. In many cases, ICS lives within a broader operational technology, OT, environment, which means technology directly involved in monitoring and controlling physical processes rather than only processing business information. That distinction is important because the priority structure often shifts in OT. In a traditional business system, confidentiality may dominate many conversations, but in ICS environments, availability, integrity, predictability, and safety often become just as important or even more urgent in day-to-day operations. If a payroll file is briefly unavailable, the organization has a serious problem. But if a control system behaves unpredictably during a live industrial process, the effect can extend beyond inconvenience into equipment damage, environmental harm, or danger to human beings. That is why ICS should never be treated as just one more network device category. IoT sits in a different part of the picture, even though it often overlaps with embedded computing and sometimes with industrial environments as well. IoT usually refers to connected devices that collect data, share status, receive commands, or support automation through network communication, often with strong dependence on remote management, mobile applications, cloud services, or centralized platforms. Many IoT devices are small, specialized, and embedded by design, but the feature that makes them feel like IoT is not just that they contain computing logic. It is that they are part of a broader connected ecosystem where device information, control, analytics, and management extend beyond the device itself. That is why smart thermostats, connected cameras, wearable health trackers, voice assistants, connected lighting, building automation sensors, and many business monitoring devices are commonly discussed as IoT. Security concerns often include privacy, remote administration, device identity, software updates, vendor trust, and the question of how much data leaves the local environment for cloud-based processing or control. The device may be small, but its trust relationships can extend surprisingly far. One of the most important things a beginner can learn is that these categories overlap, but they are not interchangeable. Many ICS components contain embedded systems, and many IoT devices are embedded systems too, but not every embedded system is part of ICS or IoT. A controller inside an automobile braking component may be embedded without being part of a broad cloud-managed IoT platform. A factory motor controller may be embedded and part of ICS without sharing the consumer-oriented behavior people often associate with IoT. A smart home camera may clearly be IoT and embedded, but it usually does not belong to ICS because its role is not controlling an industrial process. The boundary becomes clearer when you ask what the device is for, what it connects to, what it can influence physically, and what happens if it fails, lies, stops responding, or receives malicious instructions. Security becomes much more realistic when you stop sorting devices by size or appearance and start sorting them by operational role, connectivity model, and consequence of compromise. A few examples make the difference much easier to see. A microwave oven contains embedded logic that manages time, power levels, and user input, but it may not be networked at all, which means it is an embedded system without necessarily being IoT. A smart doorbell is also embedded, but it typically sends video outward, relies on a mobile application, communicates through a broader service platform, and receives configuration changes remotely, which places it much more clearly in the IoT category. A conveyor control component in a manufacturing plant may also be embedded, but if it helps regulate motion, sequencing, or process conditions in a production environment, it falls into ICS territory because it participates directly in operational control. A building may also contain connected climate controls that look like IoT at one layer and operational systems at another, especially when they affect core services or safety conditions for a facility. These examples show why boundary recognition is not just about naming technology correctly. It is about understanding which security assumptions are appropriate and which ones become dangerous if copied carelessly from the wrong environment. These boundaries matter because security priorities shift once the device's role changes from convenience, computing, to physical process dependence or large-scale remote connectivity. In many ordinary information technology, IT, conversations, people focus first on protecting sensitive data, preserving account security, and maintaining normal business operations. Those goals still matter for embedded systems, ICS, and IoT, but they do not always dominate the same way. An IoT device in a consumer setting may raise major privacy questions because it gathers presence data, audio, location, or visual information that leaves the local environment. An ICS component may raise stronger concerns about process reliability, safe operating conditions, predictable timing, and protection against unauthorized changes that could disrupt physical equipment or human safety. Even a non-networked embedded device may matter greatly if software error or unauthorized modification could affect braking, heating, dosing, access control, or some other important function. When beginners understand the boundary, they also understand why security success cannot be measured by one universal question. The right question depends on what the system is trusted to do in the real world. The boundary between IT and OT is especially important because many modern organizations want business visibility into industrial or operational environments without fully appreciating the security trade-offs that come with that connection. A company may want production dashboards in corporate offices, maintenance alerts on mobile devices, centralized asset tracking, vendor remote support, or data feeds flowing into business analytics platforms. Each of those goals can be reasonable, but every added connection changes the trust boundary around the operational environment. A process that once depended on a narrower, more predictable set of local communications may begin to depend on broader network paths, shared identity systems, remote access methods, or cloud-connected services that were never part of the original control philosophy. That does not mean ICS should remain isolated forever in a rigid and outdated way. It means the organization must recognize when convenience, visibility, and business integration are stretching the boundary of a system whose failure could affect physical operations, not just office productivity. Good security starts by noticing that a bridge between environments is not neutral. It changes what kind of risk can travel in both directions. Life cycle and maintenance differences create another important boundary that beginners often miss. Many embedded systems and ICS components stay in service for years or even decades, which is very different from the fast replacement cycle many people associate with phones, laptops, and common consumer software. Some devices depend heavily on vendors for updates. Some are difficult to patch without operational disruption, and some were designed long before modern security expectations became common. In the IoT world, another problem appears at the opposite end of the spectrum, where devices may be cheap, rapidly deployed, and then poorly supported once the initial sale is over. This means the security boundary is shaped partly by how the device is maintained across time. A system that is difficult to update, difficult to test safely after changes, or likely to outlive vendor support carries a very different risk picture from a modern workstation that receives routine, centralized maintenance. Recognizing the boundary means noticing that some environments are not weak because people forgot a simple best practice. They are difficult because the device lifecycle itself places unusual limits on how quickly security changes can be introduced. Access control also behaves differently across these categories, which is another reason boundary recognition matters so much. In an ordinary IT environment, identity management may already be built around individual users, centralized directories, strong password policies, and consistent role changes. In embedded and operational environments, access may depend more heavily on specialized engineering workstations, vendor maintenance relationships, device local credentials, shared operational roles, or limited interface designs that were never built with modern enterprise identity in mind. IoT can add its own complexity through mobile apps, device pairing, cloud accounts, application programming interfaces, and remote administration portals that stretch trust far beyond the local device. The main lesson for beginners is that access is never just about who can log in. It is about who can change configuration, who can send commands, who can read telemetry, who can update software, who can reset the device, and whether those powers are separated or blended in ways that create unnecessary risk. A camera, thermostat, industrial controller, or smart lock may look simple, but the control surface around it can be much larger than it first appears. Data flow boundaries matter too, especially when devices begin sending status, logs, telemetry, images, or sensor readings outward to management platforms or cloud services. In IoT, this outward flow is often part of the product's value because users want dashboards, history, alerts, remote visibility, and convenient centralized control. In ICS, outward data sharing may start as a reasonable request for monitoring or reporting, but it can also open the door to unintended control relationships if the communication path becomes more interactive than expected. A beginner should learn to ask not only whether data leaves the environment, but also what comes back, who can influence settings from a distance, and whether the device depends on outside services to remain useful or manageable. The more the system relies on external paths, the more important the trust boundary becomes. Even when a data flow looks passive on the surface, it may still expose system identity, operational patterns, asset details, or process information that helps an attacker understand the environment better. Good security thinking treats data movement as part of the control boundary, not as an unrelated convenience feature. Several common misconceptions make this topic harder than it needs to be until they are challenged directly. One misconception is that small devices are low risk simply because they look simple, when in reality a small connected device can still expose data, provide an entry point, or influence something much larger than itself. Another misconception is that anything called industrial must already be isolated and carefully controlled by default, When many operational environments now depend on business integration, remote access, and third-party support in ways that expand exposure. Some people also assume that if a device does not store obvious business files, then it is not really a security concern, but a device can be dangerous because of what it controls, what it reveals, or how it can be misused as a stepping stone. A further mistake is treating IoT as only a consumer issue. Modern offices, warehouses, hospitals, campuses, and smart buildings all rely on connected devices that blur the line between convenience technology and mission-relevant infrastructure. The categories become much clearer when learners stop judging devices by familiarity and start judging them by function, reach, and consequence. A practical way to recognize these boundaries is to ask a series of simple but revealing questions whenever you encounter a device or system. What is its primary job, and does that job directly affect a physical process, a person's environment, or only a narrow internal function? Does it communicate beyond itself? And if so, is that communication local, organizational, cloud-based, vendor-managed, or some combination of those? What happens if the device is unavailable, gives false information, behaves unpredictably, or accepts unauthorized commands? Who owns it operationally? Who maintains it? And how easily can changes be tested without causing disruption? Does it live in a convenience setting where privacy and remote management dominate the concern, or does it live in a process control setting where stability and safety matter more urgently? These questions help you recognize whether you are dealing mainly with a standalone embedded system, a connected IoT device, an ICS component inside a broader OT environment, or some overlapping combination that needs security treatment from more than one perspective. By the end of this discussion, the most important takeaway is that recognizing boundaries is not about perfect vocabulary for its own sake. It is about learning to see that embedded systems, ICS, and IoT may share technical traits while creating very different security realities once purpose, connectivity, ownership, and consequence are taken seriously. Embedded systems describe the broad idea of dedicated computing inside larger devices. ICS points to systems involved in monitoring or controlling real-world operational processes where reliability and safety carry unusual weight. IoT points to connected device ecosystems where remote communication, data sharing, and ongoing platform relationships often shape the risk. When you can recognize where one boundary ends and another begins, you stop making one-size-fits-all assumptions that weaken security. Instead, you begin asking the right questions about what the device does, what it touches, who can influence it, and what kind of harm would follow if trust around it were misplaced. That is the foundation for much better judgment as you move deeper into modern security architecture and risk thinking.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.